Oh, no, that's calculated every time, this is inside the big loop, I think, let me double check. No, this calculates x3 for every single data point. This one, for every value in y and theta, it calculates an x3. So x3 of I will be appropriate for t of I, or whatever, you know what I mean, as it loops through. But I set t underscore y, t underscore x3, and t underscore theta equal to 0. And I set the limit as, you know, basically how far it goes is to 8. I've got a tolerance on the arriving. Basically, I'm saying it actually arrives at 8 minus this tolerance. So I wanted to make sure it caught the, if somebody had basically no overshoot, was just got almost there, was slowly creeping up on it, that they'd at least get a time. You know what I mean? And then the tolerance on theta to determine when it stops swinging, okay? The reason I set those 3 to 0 here is in the if statement, get after the pause, you'll notice I say and t of y is equal 0. Basically, it'll keep doing this if. When y finally gets greater than or equal to the limit minus that tolerance, which is 8 minus 0.01 or whatever, once y gets bigger than that, it sets ty equal to the time when that happened. Keep in mind, this I is the loop number, so y at that loop number occurred at time equal to the t at that same number, right? So as soon as y gets bigger than 8 minus the tolerance or whatever, it sets ty equal to the time that it occurred, right? But that makes it so this is no longer equal to 0. And this means and, they have to both be true. So as soon as it saves a value of time for the top getting there, ty will no longer be 0 and it'll stop checking. It won't end up setting this again. You know what I mean? It only sets it once when it first arrives. You follow what I'm getting at? I'm getting a little bit of a blank response. No, yes? Okay. When I equals 1 the first time through, right, y is probably about equal to 0, so it's not greater than. So it goes ahead and does that frame of animation. Comes back around again, y2, y3, finally gets up to y, 57 or whatever, and y is finally bigger than this. And ty is still 0 because it hadn't been set to anything yet. It was just set up there where I showed you equal to 0. So those are both true, so it goes ahead and does this, sets ty equal to whatever the time is at 57. Okay, so now it remembers what time it arrived. The next time it comes here, y is probably still bigger than this, but this is no longer true, right? Because it got set last time. Well, they both have to be true for this if statement to do what's inside. And this one's not true anymore, so it stops doing it, doesn't do this anymore. It just remembers that first time. This works the same way with x3. When x3 is greater than the limit, and tx3 is equal to 0, when it finally gets up to the number I where x3 is greater than, it sets tx3 equal to the time at that point. And then from then on, tx3 is no longer equal to 0, it's equal to the time where it first got there. So since these both, this and, both have to be true, then it saves when it first got there and never changes it. Okay. This right. Anytime theta is greater than the theta tolerance, which was like 0.005 or something, right? That means it's swung outside the angle tolerance. And I use absolute values, so either way it swings. anytime this is bigger, it sets this equal to that time. Follows it up by saying if the current time minus the one that got saved, right? As soon as this gets back down inside the tolerance, it stops saving the time, right? But this one keeps increasing. So you're measuring the time between now and the last time it was outside the tolerance. Remember the definition of the you got something that's going like this, and you've got a tolerance, right? And the settling time or whatever is the point at which it no longer goes outside the tolerance. That's what we're looking for. Well, every time it goes outside the tolerance here, that variable t underscore theta gets set equal to that time, right? The next if statement. So let's say it remembers this, it's remembering these points, right? When it gets to here, it stops, it's inside, so it stops remembering, right? So the current time minus that time tells you how long it's been since the last time it went outside the tolerance, right? If that time that it's been outside the tolerance is greater than the theta cycle, which I set up there to be 3/2 pi times the divided by the damped frequency that we calculated. So that's the amount of time for it to go, not 2 pi, but 1.5 pi cycles, right? You could say 2 pi. Basically, once it gets longer than a full cycle, that means it's not going to go outside anymore. See what I mean? When it gets to where, let's say it remembers this point, right? That point, let's say, just goes barely outside. So it remembers that point. You get over here, basically 1.5 cycles later, if it hasn't gone back outside, it's not going to go back outside, right? So once that happens, that's where this is greater than that 3/4 pi or 3/2 pi divided by the damped frequency. So it's going to give you the number of seconds for it to go through 1.5 pi cycle, almost a full cycle. Once it's past that and the Ty is greater than 0, which means it actually, the top went past the limit. This one means the bottom went past the limit, right? Or I say, whoops, that was supposed to be. Oh yeah, this is if it goes off the screen and keeps on going. I had at least one that just took off. If y gets greater than 10 times the limit, just give up, because it's not coming back, okay? And you'll notice I've got an extra set of parentheses, so all these have to be true, or, that's what this means, that's true. So, if it's gone more than 1.5 pi cycles without going outside, and it's arrived, both the top and the bottom have actually reached the limit, then break makes it stop animating. Or if it goes past 10 times the limit, it stops animating. That's what this break command breaks it out of the loop. Okay. Once it breaks out of the loop, then I calculate the overshoot, which is that max of the max, right? Get the max of the y, the max of the x3, the max of either one, find out which one's bigger, subtract 8, divide by 8, multiply by 100. I am just formatting a display the one you saw on the screen. This is for the 2 times, and the ended time, I did a VPA on it. And then this, if you look in display equation script I gave you, is kind of a copy. It basically puts that, I don't know if I still have a window left over. It does kind of a display equation of that, you know, these items that I had in the square brackets. But it does it on the graph instead of a separate window. So I just kind of pulled out the extra commands, pulled out the commands necessary to do it from, and let's see, if you want, yeah, see the rest of that one. Okay.
And we had this to show blinds?
Yes,
Okay.
yeah, just to show blinds. This basically converts this equation box, or what, you know, the same thing we do with the equations, where you get the square brackets and the various equations, right? This converts it to what's called latex, and then this over here